In this video, we are going to talk about the Coulomb's law. So let's assume that we have an atom. Now, an atom is made up of protons and then electrons. So if the number of protons in the atom are greater than the number of electrons, then we have a net positive charge on the atom. But if the number of protons are less than the number of electrons, then we have a net negative charge. Now, if we have a proton and then we bring it near an electron, it is going to experience a force. And because they are unlike charges, the force is going to be an attractive force. So there's going to be a point of a force of attraction between these two charges. Nonetheless, if we put either a proton and then a proton near each other, or an electron and an electron charge near each other, then these two cases, they are going to experience a force of repulsion between the 2 point charges. Now, until Coulomb, it was difficult to determine the magnitude of the force that these two charges will exert on each other. So Coulomb came up with that law, which is known as the Coulomb's law, where he said that the magnitude of the force of attraction or repulsion between any 2 point charges is given as F equals K, where K is a constant, then the first charge, then times the second charge divided by the square of the distance between them. So Coulomb's law is an inverse square law. Now, if you remember Newton's gravitational force, which says that the force of attraction between two bodies is given by the Newton's gravitational constant times one of the masses, the first mass times the second mass of the object divided by the square of the distance between them. So it is similar to this law. Now, if we have more than two systems of charges and want to determine the force between those system of charges, then we need to take the algebraic sum of all the forces. The charge of an electron is given by 1.6 times 10 exponent minus 19 coulombs. Charges are always conserved. So let's take some problems and then understand this law into details. Two particles attract each other with a force of magnitude F acting on each other. If the charge of one is double and the distance separating the particles is also half, the force acting on each of the two particles has magnitude. Then they've given us all the possible answers. That is A F over 2, B F over 4, C F, D 2F, and E 8F. Now, from Coulomb's law, so we have two particles and they attract. So since they attract each other, we know that they are of opposite charges. So we have a system of a positive charge and then a negative charge. Now, they will attract each other with a force F. Now, based on Coulomb's law, we know that the force of attraction is given by F equals a certain constant times, let's assume that the charge on this one is Q1 and then the charge on this is Q2. So it's going to give us Q1 times Q2 divided by R squared, where R is the distance between the centers of the charges. So that's the force of attraction between these two when nothing happens. But at the second part, it says that the charge of one is doubled. So we have one of these charges doubled and the distance separating the particles is also halved. So now, so this is the initial force, let's say Fi. Now the final force, Ff, is the constant, then one of these charges. So let's say that now Q1 becomes 2Q1 because it is doubled, then times Q2 divided by, and this distance is also half, so R becomes half R or square. So So ff is equal to, now let me pull this constant out, so it becomes 2k, then q1 q2 divided by, now 1 over 2 squared is 1 over 4, then r squared. So ff is equal to, this 1 over 4 go to the top, so it becomes 8k q1 and q2 times the square of the distance between them. Now remember that we said that the initial force is what? kq1 q2 divided by r square. See here, kq1 q2 divided by r square. So it means that the final force is equal to 8 times the initial force. So we have 8f, and then if you look through the answers, you see that E is the answer with 8f. So the answer is E. So it means that the force acting on the two particles will be multiplied by a factor of 8. A point charge of 3 times 10 to the minus 6 coulombs is 12 centimeters distant from the second point charge of minus 1.5 times 10 to the minus 6 coulombs. Calculate the magnitude of the force on each charge. So it's similar to what we did initially. So let's assume these are the 2 point charges. The first one is, so q1 is equal to 3 times 10 exponent minus 6 coulombs. And then let's say this is q2, that is minus 1.5 times 10 exponent minus 6 coulombs. And the distance between them is 12.0 centimeters. So based on Coulomb's law, we know that the force between them is F equals, so F12, that's equal to the first charge Q1, but then a constant K, then times Q2 divided by the square of the distance between them. So F12 is equal to, K is 9 times 10 exponent 9, then times the first charge, which is 3 times 10 exponent minus 6, then times the second one, which is minus 1.5 times 10 exponent minus 6, divided by the square of the distance between them. Now 12 is the same as 0.12 meters squared. So if you do all of this, F12 is equal to minus 2.81 newtons. 2 point charges are located on the positive x-axis of a coordinate system. Charge Q1 equals 5 microcoulombs, is 4 centimeters from the origin, and charge Q2 is minus 3 microcoulombs, is 7 centimeters from the origin. What is the magnitude of the total force exerted by these two charges on a charge Q3, which is equal to 4 microcoulombs located at the origin? Gravitational forces are negligible. So the first thing is that they are all located on the positive x-axis, and therefore let's first start with the origin. So this is charge Q3, this is the one which is located at the origin. So Q3 equals, and it is 4 microcoulombs. So this is 4 microcoulombs. And then we have the second charge. The second charge is the first one, which is Q1, 5 microcoulombs, and it's 4 centimeters. So here is 4 centimeters. And then we have Q1. So this is Q3. Q1 equals 5 microcoulombs. And then we have the third charge. This is the third charge, which is Q2. And this Q2 is minus 3 microcoulombs. And it is also 7 centimeters from the origin. But since here is 4 centimeters, it means that the distance here is 3 centimeters. So that when you add it, you get 7 centimeters. So based on Coulomb's law, we know that because of these two charges, there's going to be a force of attraction between these two, and that will be F13. And then there's also going to be a force of attraction between these two, which is this charge, third charge, and then the second charge. So we also have F23. But from the question, the reason why we will not consider this charge, which is F12, between these two charges, is that the question only said we should find the charge, the forces that these two charge exert on this third charge. So that means that the question didn't ask for this force, and that's why we are not concerning ourselves on that force. So now, based on Coulomb's law, we know that the force is given as F equals a certain constant times one of the charges. So let's say QA times the second charge QB divided by the square of the distance between them. So let's start with F13. Now this K, which is this constant, is given as 9 times 10 exponent 9, then times the first charge 1, which is 5 microcoulombs. So it's 5 times 10 exponent minus 6, then times the second one, which is the charge at the origin, 4 microcoulombs. So 4 times 10 exponent minus 6, and divided by the square of the distance between them is 4 centimeters. 4 centimeters is the same as 0.04 meters, so 0.04 square. So F13, if you compute all of this, we are going to get 112.5 newtons. Now let's come to this force, which is F23. So it's the same thing. So it's going to give us K. K is 9 times 10 exponent 9, then times the second charge 2. 2 is minus 3 microcoulombs, so it's minus 3 times 10 exponent minus 6, and then times the charge at the origin, which is 4 microcoulombs, so 4 times 10 exponent minus 6, divided by the square of the distance between them, and this is now is 7 centimeters, which is the same as 0.07 meters squared. So we find out that F23 is equal to, if you compute all of this on the calculator, now remember that there's a minus here, so it's going to give us a minus answer. So it's minus 22.04 newtons. Now, so the force on Q3, so let's say F, which is the total force that these two charges exert on Q3, is going to give us F13 plus F23. So we have to sum them algebraically, but because they are all located on the positive x-axis, then we can just sum these two. So F is equal to 112.5 newtons minus 22.04 newtons, and if you do this, you are going to get 90.5 newtons. 3 charges, Q1 equals plus 2 microcoulombs, Q2 equals plus 3 microcoulombs, and Q3 is plus 4 microcoulombs, are placed at the corners of an equilateral triangle of side 20 centimeters, as shown in the figure. Determine the magnitude of the forces exerted on Q3 by Q1 and Q2. So we want to determine the force here that is being exerted by Q1 and then Q2. So now we just need to use the Coulomb's law. So from Coulomb's law, the force is equal to a constant times the first charge times the second charge divided by the square of the distance between them. So now F is equal to the force exerted on Q3 by Q1, so it's F13, then plus the force exerted on Q3 by Q2, which is F23. Now let's first find F13. So it's equal to, now the K is 9 times 10 exponent 9, then times 1, the first charge. So Q1 is 2 microcoulombs, so 2 times 10 exponent minus 6, then times the third charge, Q3 is 4 microcoulombs, 4 times 10 exponent minus 6, divided by, now the distance between them is 20 centimeters, which is the same as 0.2 meters squared. And then if you compute this, you are going to get 1.8 newtons. So let's look at the case of F23. So that's equal to the same constant, 9 times 10 exponent 9, then times the second charge, Q2, and then Q2 is 3 microcoulombs, so 3 times 10 exponent minus 6, then times the third charge, Q3, which is 4 microcoulombs, 4 times 10 exponent minus 6, divided by the square of the distance between them, 0.2 square. And if you compute this on a calculator, you are going to get 2.7 newtons. Nonetheless, we cannot just add these two forces. The reason is because we are talking about the case of an equilateral triangle. So therefore, we need to add the two forces algebraically. But we know that since it's an equilateral triangle, the angle between the angle here is 60 degrees. Then the angle here is also 60 degrees. And the angle here is 60 degrees. So what it means is that F is equal to this one, which is the 1.8 newtons. So 1.8, and then we need to add cos 60 and then sine 60, then plus F23 is 2.7 newtons, so 2.7, then cos 60 sine 60. So this is how to add them algebraically. So F is equal to, now 1.8 cos 60 is 0.9000, and then 1.8 sine 60 is 1.588, and plus cos 60 is 2.2500, and 2.7 sine 60 is 3.8970. Sorry, here is 1.35 and here is 2.33082. So sorry for the correction. And if you add all of them, 2.2500 here and then 3.897. So now we need to find this force. So the force F is going to give us, we just have to find the magnitude of this vector, which is 2.25 squared, then plus 3.897 squared. And if you do this, you are going to get 4.49 newtons. How many electrons will have to be removed from a penny to leave it with a charge of plus 1.0 times 10 exponent minus 7 coulombs? And then the B part says that to what fraction of these electrons, yes, these electrons in the penny does this correspond? The penny has a mass of 3.11 grams, and we must assume that the penny is made entirely of copper. So we know that the electron charge is a conservative charge. So what it means is that the total charge on a system of electrons is equal to the number of electrons that are there times the charge of the electrons. So in this case, we are talking about how many number of charges are going to sum up such that we are going to get 1.0 times 10 exponent minus 7 coulombs. So it means that the total charge here, Q, is 1.0 times 10 exponent minus 7 coulombs. And it's equal to the total number times the electron charge. The charge of the electron is 1.6 times 10 exponent minus 19 coulombs. So yes, coulombs. So N in this case is equal to 1 times 10 exponent minus 7 divided by 1.6 times 10 exponent minus 19. And if you do this, you are going to get 6.25 times 10 exponent 11 electrons. So these are the total number of electrons in that system that will sum up to this value. So the B part says that to what fraction of these electrons in the penny does this correspond to? Now, to be able to know the fraction that this corresponds to, we must first know the total number of electrons in the penny. So let's first find the total number of atoms in the penny, but we can find it by first finding the total number of moles. So we know that number of moles of copper is equal to the mass of the copper, then divided by the molar mass of copper. So the mass of the copper was given as 3.1 times 3.11 grams divided by the number of moles. Sorry, the molar mass of copper is 63.5 grams per mole. So if you compute this, you are going to get 0.049 moles. Then now let's find the total number of atoms. So total number of atoms, and this is equal to the number of moles of copper times the Avogadro's constant. So this is equal to the number of moles of copper is 0.049 moles. Then the Avogadro's constant is given as 6.02 times 10 exponent 23 atoms. And if you compute this, you are going to get 2.945 times 10 exponent 22 atoms. So these are the total number of atoms in the penny. But the penny is made up of copper. So since it's made up of copper, it means that each atom in the penny is going to have the same number of electrons as each atom of copper has, and the atomic number of copper is 29. So it means that the total number of electrons is equal to 29 electrons per each times the total, which is 2.945 times 10 exponent 22, and that will give us total number of electrons of 8.54 times 10 exponent 23 electrons. So I'm putting electrons here for electrons. So the fraction is equal to the total number of electrons, the number of electrons we got in the first case, which is 6.25 times 10 exponent 11 electrons, divided by the total number of electrons, which is 8.53 times 10 exponent 23 electrons. And if you do this, you are going to get 7.318 times 10 exponent minus 13. So that is a fraction. A certain charge is divided into two parts, Q and then Q minus small q, which are then separated by a distance. What must Q be in terms of capital Q to maximize the electrostatic repulsion between the charges? So now we know that the charge has been divided into small q and Q minus Q. So in other words, we have two charges which are separated by this distance r. So one of them is Q, the second one is capital Q minus small q. So the force of attraction, so the force between them, F, is equal to Q times capital Q minus small q times this constant K divided by the square of the distance between them, R. So F is equal to K times Q small q minus Q squared divided by R squared. But from the question, we want to maximize the repulsion between them. So this repulsion will occur at where the maximum will occur at where the F the Q is equal to 0. So let's find the F in the Q. That is equal to K. If you differentiate this with reference to small q, you get capital Q. And if you differentiate Q squared reference to small q, you get minus 2Q divided by R squared. So at where the F the Q is equal to 0, this cannot be 0 except capital Q minus 2Q is equal to 0. So let's make small q the subject. So 2Q is equal to capital Q, and therefore small q is equal to capital Q divided by 2. So the maximum electrostatic force of repulsion will occur at where small q is equal to capital Q divided by 2. It must be the distance between point charge Q1 equals 26 microcoulombs and point charge Q2 equals minus 47 microcoulombs for the electrostatic force of repulsion between them to have a magnitude of 5.7. So we have 2 point charges. So this is charge 1 and then this is charge 2. So charge 1 is equal to 26 microcoulombs. And then the second charge Q2 equals minus 47 microcoulombs. And then the distance between them is what we are looking for. And then the magnitude of the force F is equal to 5.7 newtons. So from Coulomb's law, we know that F is equal to K times Q1 times Q2 divided by R squared. So in this case, we need to make R the subject. So R is equal to the square root of K Q1 Q2 divided by F. So R is equal to, nonetheless, we cannot have a negative distance, and therefore this minus 47 microcoulombs, we are going to take the absolute value of it. And also, we cannot find the square root of a negative number, else we will run into imaginary numbers, and distances are not imaginary. And therefore, this is equal to the square root of K is 9 times 10 exponent 9, then times Q1, which is 26, times 10 exponent minus 6, then times the second charge, which is 47 times 10 exponent minus 6, divided by the force, and the force is 5.7 newtons. So R is equal to 1.39 meters. The second part says that in a fission, a nucleus of uranium-238, which contains 92 protons, divides into 2 smaller spheres, each having 46 protons, and a radius of 5.9 times 10 exponent minus 50 meters. What is the magnitude of the repulsive electrostatic force pushing the 2 spheres apart? So we have 2 spheres here. And then the radius of each sphere is this value, which is 5.9 times 10 exponent minus 50 meters. So we have here, so let's say here's R1 and here's R2, and then there are 46 protons each. So we have 46 protons here, and we also have 46 protons here. So we want to find the force pushing these 2 apart. So using Coulomb's law, F is equal to the constant 9 times 10 exponent 9, then times the first charge, but there are 46 protons, so it's going to give us 46 times 10 exponent minus, 46 times the charge of the proton. The charge of the proton is 1.6 times 10 exponent minus 19. Then times this one, which is the same thing, 46 times 1.6 times 10 exponent minus 19, divided by the square of the distance between them. Now the distance is from center to center, so it's going to be twice this radius, because it's going to be this one plus R2, and it's going to just give us 5.9 times 10 exponent minus 15 then plus 5.9 times 10 exponent minus 15 all squared. So F is going to give us, if you compute all of this, it is 7.3 times 10 exponent minus 18 newtons. Two identical spheres fixed in a place attract each other with an electrostatic force of 0.108 newtons when separated by 50 centimeters center to center. The centers are connected by a wire. When the conducting wire is removed, the spheres repel each other with an electrostatic force of 0.036 newtons. What were the initial charges on the spheres? So we have these two spheres. Since they attract each other, then they are spheres of opposite signs. So let's put the spheres here. And then the distance separating these two spheres is 50 centimeters. So now, they also give us the electrostatic force of attraction, which is 0.108 newtons. So we have F equal to 0.108 newtons. So we want to find the charges on the spheres. That is the initial charges on the spheres. This is very important. So now we know that from Coulomb's law, the force is equal to Q plus then times Q minus divided by R squared. However, there is a constant here. So if we make Q plus and Q minus the subject, we see that Q plus times Q minus is equal to FR squared over K. So Q plus times Q minus is equal to, now the force was giving us 0.108 newtons and the distance separating them was 50 centimeters, which is the same as 0.5 meters, divided by K, 9 times 10 exponent 9. And if you compute this, you see that Q plus Q minus is equal to, but I made a mistake. Since the forces attract each other, it means that F is a negative force. So that will give us minus 3 times 10 exponent minus 12 coulombs because of the force of attraction. So we need to put minus here. So now, the second part of the question says that the spheres are connected by a wire. So if it is connected by a wire, there will be redistribution of charge, such that the total amount of charges in this sphere will be equal to the total amount of charges here. And therefore, Q plus times Q minus we're just going to give us Q times Q, which is Q squared, because the redistribution of charges makes the charges here equal to the charges here. So therefore, but in that second case, you see that they repel each other, and therefore this force is no more negative. It's now a positive 0.036 newtons, but the distance remains the same. So in this case, Q plus times Q minus, which is equal to Q squared, is equal to the same thing, the force, and in this case the force is 0.036, then times the distance between them, 0.5, divided by the constant 9 times 10 exponent 9. So Q is equal to the square root of 0.036, then times 0.5 divided by 9 times 10 exponent 9. And if you compute that, you find out that Q is equal to 1 times 10 exponent minus 6 coulombs. So that is the value of the charges when the wire is connected. But from the question, we are supposed to find the value of the initial charge. So Q is 1.1 times 10 exponent minus 6 coulombs. Nonetheless, remember that there was already charges on the Q plus before charges flowed from Q minus to the Q plus. So therefore, Q plus in this case is just going to be twice of this Q. So 2 times 10 exponent minus 6 coulombs. But the question says that we should find the initial charges that were on the spheres. But we know that Q plus times Q minus is equal to minus 3 times 10 exponent minus 12 coulombs. So the initial charge, which is Q plus, that was on the sphere, is equal to this new value minus Q minus that flowed into the Q plus when the wire was connected. So that is 2 times 10 exponent minus 6, then minus Q minus, then times Q minus, and that is equal to minus 3 times 10 exponent minus 12 coulombs. So if we expand this, we find out that we have this as 2 times 10 exponent minus 6 Q minus Q minus squared, which is equal to minus 3 times 10 exponent minus 12. So this is the equation we got from the previous step. So we need to use the quadratic formula, because you can see that this equation is of the form ax squared plus bx plus c equals 0. So using the quadratic formula, x is equal to minus b plus or minus square root of b squared minus 4ac divided by 2a. So q is equal to minus b, so minus minus, we make this plus. So we have 2 times 10 exponent minus 6 here, and plus or minus square root of b squared, which is minus 2 times 10 exponent minus 6 squared, then minus 4 times a is 1, then times c is minus 3 times 10 exponent minus 12. All of this divided by 2 times 1. And if you do it, you find out that, here was Q minus. So you find out that Q minus is equal to 2 values, which is 3 times 10 exponent minus 6 coulombs, or minus 1 times 10 exponent minus 6 coulombs. So having found Q minus, remember that we said that Q minus times Q plus is equal to minus 3 times 10 exponent minus 12. So if Q minus is equal to 3 times 10 exponent minus 6, and Q plus is equal to minus 3 times 10 exponent minus 12, we are just making Q plus the subject here, divided by Q minus, which is 3 times 10 exponent minus 6. That will give us minus 1 times 10 exponent minus 6 coulombs. Or if Q minus is equal to minus 1 times 10 exponent minus 6 coulombs, then we find out that Q plus is equal to minus 3 times 10 exponent minus 12 divided by minus 1 times 10 exponent minus 6, and that's equal to 3 times 10 exponent minus 6 coulombs. So we either have Q minus is minus 1 microcoulombs, and the Q plus is 3 microcoulombs, or Q minus is 3 microcoulombs, and then Q plus is minus 1 microcoulombs. So it says that 3 identical point charges, each of mass 0.1 kilograms, and charge Q hang from these 3 strings as in the figure above. If the length of the left and the right strings are 30 centimeters at an angle of 45 degrees. Sorry, at an angle of 45 degrees, and determine the value of Q. So this length is L equals 30 centimeters. So here is 30 centimeters, and here is also 30 centimeters. Then here is 45 degrees. Then here is 45 degrees. So having these two, the first thing we can find is we can find the distance here. And then we can also find the distance here. Now remember that sine theta is opposite over hypotenuse. So therefore, the length here, let's assume the length here is maybe A. Then we can find out that A is equal to 30. Sorry, so we need to convert it to meters. So 30 centimeters is the same as 0.3 meters. So 0.3 is sine 45. And if you do that, you are going to get 0.212 meters. So the distance here is 0.212 meters. And the one here is also 0.212 meters. But then what we are looking for is the value of the charges, which is Q. However, you can see that there is a mass here, and this mass is acting downwards. And we're given the mass 0.1 kilograms. So we can find the weight of the point charge. So the weight of the charge is equal to the mass times gravity. And then the mass was given us 0.1 kilograms. So 0.1. And gravity is always 9.81. And if you compute that, you are going to get 0.981 newtons. So we have this mass here, so this force is acting downwards at 0.981 newtons. But remember that from Newton's third law, there is also a reaction force here which is acting upwards, and it is equal and opposite to this force. However, because this is a string, we need to remember that there is a tension in this string, and there is also a tension in the string. Now, the horizontal component of this tension is, it is going in this order. So this horizontal component is T cos theta, and then the vertical component is T sine theta of this tension. But you see that this T sine theta is equal and opposite the weight. So based on Newton's third law, so from Newton's third law, we can then conclude that T sine theta is equal to the weight, and the weight we got as 0.981 newtons. So T is equal to 0.981 divided by sine 45 degrees. And if you compute that one too, you are going to get 1.39 newtons. So it means that we can find the horizontal component of the tension, which is Tx. So it's just going to be 1.39 cos 45, and that will also give us 0.983 newtons. However, you can see that this force is so you can see that the charge here is positive and the charge here is positive. So there is a repulsive force between this charge and this charge. There's also a repulsive force between this charge and that charge. Now you see that they are going in the negative x direction. So this is minus F. So let's say here is 1, 2, and then 3. So here is minus F13, and this one too is minus F23. But the horizontal component of the tension is going the positive x direction, so that one remains. So what it means is that Tx then plus minus F23, and then also plus minus F13. We are summing all the forces acting on this charge is equal to 0. because they are collinear forces. They are acting at this point. So if you sum all the horizontal forces acting on this point charge, that will give us 0. And that is this expression. So it implies that Tx minus F23 minus F13 is equal to 0. So Tx is equal to F23 plus F13. So let's find F23. F23 is equal to the charge K, and then the charges we don't know, but they are equal charges. So Q squared divided by the distance between this charge and this charge is 0.212. So here is 0.212 squared. And then I made a mistake. Here is supposed to be F12, because we are talking about this charge. So F12 and F13. So here is F12 and then F13. So let's change all of this. The 3 becomes F12, then F13. So let me rewrite this. F12. Now let's talk about F13. So here's F12. F13 is equal to, it's the same thing. So KQ squared, then divided by, however, this distance will change because it's going to be this distance plus this distance. So 0.212 plus 0.212 squared. And that's going to give us KQ squared divided by 0.41424 squared. So Tx was given as 0. We got Tx as 0.983 equals K, and K is, so we are factorizing KQ out. So KQ squared, then this would be 1 divided by 0.212 squared and plus 1 divided by 0.424 squared. So if you make Q the subject, Q is equal to, Q squared is equal to, now 0.983, and if you solve this, you are going to get 27 divided by 9 times 10 exponent 9. So if you find the square root of both sides, this one and this one will cancel, and if you compute this, you find out that Q is equal to 1.98 times 10 exponent minus 6 coulombs, which is the same as 1.98 microcoulombs. So it means that the charge on each of the spheres is 1.98 microcoulombs.